Well, welcome back. And we are now going to attempt to do 3 pages of what I call extras. These are also sheets you're going to want to study very carefully to prepare you for the final exam. All right? So we may not do extra page 3 today, but let's see how far we get. And if I feel that we have not used up too much time, I might have us do the extra page 3 today. For sure, we're going to do pages 1 and 2. I'd just like to remind you that your homework is going to be for the weekend to try exam review sheets 2. There are 4 of them, okay? So I will remind you of this once we have completed or get to the end of this video. So here we go. Are you ready? We're about ready to tackle this next set of sheets. So here we go. I'm going to share a screen here with us now, okay? And our first question we're going to see is a very familiar one, okay? We have spent time talking about this principle a lot in this course, and so we're going to talk about it again on the final exam. Soon there are 3,850 babies ranging in age from 1 to 5, all right, years old, and they're sent to a clinic and are vaccinated against a particular disease. Explain why we know that at least 2 of these babies were born on exactly the same date, month, day, and year. Wow. Well, you can guess probably what the principle is we're going to use on this, right? It's probably going to be PHP, baby, all right? The pigeonhole principle. But to show that it's a pigeonhole principle, we need to give some background. And for me to give you full credit for this problem, you can say PHP, all right? Now you know it's PHP, baby, but we want to know why. Well, there's 3,850 babies, and their ages are from 1 to 5. So that's 5 different years worth of babies that were born, okay? How many days are there available for these kids to have been born on over 5 years? Well, that's the first thing we've got to figure out, okay? So using dimensional analysis to help us, if we take 5 years worth of days, okay, we know there are 365 days in a year, right? So how many days are available for these people to have been born on in that 5-year period of time? Well, all we have to do is take 365 days, take your calculator, times 5, and we find that there's 1,825 potential birth dates over the 5-year period of time. So, therefore, what do we definitely know? We definitely know there are more babies than there are dates for them to be born on. Therefore, what has to happen? Duplication of birth dates absolutely has to happen, right? So how would we say that? There are more babies than birth dates. Therefore, duplication of birth dates has to occur. Okay? Now you know I'm going to put that on the final, something like that. Okay? So that is our question today in relation to PHP, all right, pigeonhole principle. We know because of the pigeonhole principle, there have to be babies that were born on the same birthday if there's only 1,825 potential birth dates that we could have. All right, let's go on to the next question. Now, the next question, okay, is a little bit difficult and one that maybe you might not think of. But you will recall we talked earlier this year about the fact, or this semester, about the fact that there is a law of mathematics which basically says the whole is always equal to the sum of its parts. So in this particular problem, what we're going to do is we're given the area formulas that are shown here, and we're going to informally prove that the whole is equal to the sum of the parts by verifying that the individual areas of the parts labeled A1 and A2 indeed equal the area of the large triangle XYZ. Carefully show your work. I gave you a whole bunch of information about this figure. RT is parallel to ZY. UX is equal to 36 millimeters. UV is equal to 36 millimeters, and so forth. You can read them there. And remember, the formulas for a triangle and a trapezoid are given here for you to use. Let's determine if the parts, A1 and A2, if their areas are exactly the same put together as the whole triangle here, XYZ. So let me move this down. Now, I think the simplest thing maybe to do would be for you to take your figure and, if you can, label the various dimensions of it that you're going to need, okay? Now, because RT and ZY are parallel to each other, you know that the figure on the bottom, RTYZ, has to be a trapezoid, right? It has a pair of parallel sides, okay? And it obviously is a trapezoid. The triangle on top, RXT, obviously is a triangle, okay? And we have information about each of these figures so that we're able to find their areas. So let's concentrate on finding first the area of triangle XTR. So over here, I'm going to go triangle XTR. Now, what are its dimensions? Well, you can see that there is a height, a dotted distance, XU, which represents the height of the triangle that is drawn perpendicular to what we would call the base, RT. So from R over here to T, we know, looking at our information given to us, that this is 90 millimeters. We know the height of the figure, okay, is what? Well, that's UX, right? UX is 36 millimeters. So this distance right here is 36 millimeters. I don't know if you can read that, but that's 36. All right, how do I get the area of the small triangle on top? The formula is simply A equals 1/2 base times height, right? And to get that, I will simply do A equals 1/2. The base of the figure is 90. The height of the figure is 36. And the answer will be in square millimeters. I know that. So I'll put that. And now all I have to do is multiply those three together. Well, you know 1/2 of 90 is 45, right? So if I take 45 times 36, I obtain the area of this is 1,620 square millimeters, okay? So we've got one of the pieces. This is A number 1, okay? All right, let's tackle A number 2, all right? Well, that's a little harder figure. It's a trapezoid, right? But to get the area of the trapezoid, all I simply have to do is use its area formula. This is for area 2. It is 1/2 its height multiplied by the sum of its bases. All right? So to obtain area 2, I will simply do 1/2, all right, times the height of the figure. The height of the figure is also 36. I did say up above that UV is 36, okay? And the sum of its bases, well, the top base is 90. I have that labeled, right? What is its bottom base? Well, if you look up at the data I gave you, ZY is twice as long as the 90, so it's 180. So if I work this out to get area 2, I simply do 1/2 of 36 times 90 and 80 adds up to 270. Well, of course, you realize that half of 36 is 18. So I'm going to multiply 18 times 270 over here on my calculator. 18 times 270. And when I do that, I get 4860 square millimeters of area. So there are my two pieces. Okay? Now, what's the area have to be of the great big rectangle XYZ? So next I'm going to deal with XYZ, all right? And so I'm going to call that area, I'm just going to call it Z. The area of Z figure, the XYZ figure, has got to be 1/2 base times height, right? Area, I'm going to call it Z, has to be 1/2. Well, what is its base? Well, its base is the distance, ZY, which is 180, and its height is 2 lengths of 36, right? UV is 36, XU is 36. This is 36 right here, just like the other one is 36. So that will be 72, okay? So to get the area of XYZ, I simply do, well, I'm going to take 1/2 of 180, which is 90, and I'm going to do 90 times 72 on my calculator. So I simply do 90 times 72, and when I do, I get 6480 square millimeters, okay? Now, is the area of triangle XYZ equal to the area of the other two pieces put together? Well, let me extend this a little bit, move it back up here, and let's find out. Well, area 1 plus area 2 should be the answer that we got for the area of XYZ. Here we got 6480. So I'm going to add area 1, 1620, plus area 2, 4860. Do I get 6480? Well, if I take 1620 and add to it 4860, I do get 6480. So 6480 square millimeters here is exactly the same as 6480 square millimeters here. Therefore, it checks out. QED. I have shown that the whole is equal to the sum of its parts. Now, this was a fairly simple figure. I'm going to give you a problem like this on the final exam. However, the figure is going to be more complicated, but you get the drift of what you have to do. You have to get the areas of the pieces and show that they are equal to the area of the entire large figure that the pieces make up, okay? So you can look forward to the fact that you will see one of these on the final exam, okay? All right, let's go on. Now, I would like to take a look at a bunch of thought questions that are going to be on this final. The reason I am putting these thought questions on here, these true, false thought questions, is to make you think about things we've talked about in this course. You're going to notice some weird stuff, okay? In the sheet I have had you print, you will notice there are some holes in the words, like here, okay? You will notice that because of the conversion of taking this sheet and making it into a PDF, if for some reason, if a letter T and I are next to each other, it leaves them out. So I had to put spaces. Notice the word irrational down here is spelled in a kind of a funny way too. I did that because of the fact that the PDFs would just not make, it would not make them correctly from the software I was using. So therefore, maybe it's the font, I don't know. But therefore, I made the sheet look a little strange, so don't be surprised. Now, what I'm going to show you is not going to look strange. It is the way it should be, but I couldn't make a PDF out of this to show you. Now, what I'm going to do is I'm going to read each one of these examples to you, okay? And I'd like you to read it to yourself. Then I'm going to give you a couple of seconds to think about it. Then I want you to write down what you think the correct answer is, true or false. Okay, T for true, obviously, F for false. And then we're going to go over each question. If a first event in a combination probability experiment has 75 outcomes, it is followed by a second event that has 40 outcomes, the two events combined must have 115 outcomes. Now, if you add 75 and 40 together, okay, you do get 115. However, that is not the correct answer. This is false. The correct answer is you must what? Multiply the number of outcomes together. 40, I said 17, I'm sure I meant 75. You have to multiply 40 times 75. So the number of outcomes here is what? 3,000 different outcomes. Okay? So the first answer was definitely false. Okay, let's go to number 2. The set of rational numbers does not contain any whole numbers or counting numbers. All right, here's the counting number 13. Can I write it as a fraction by putting it over 1? I can, right? What's that tell you? That tells you that 13 is definitely a what kind of number? Rational, right? Now, is the number 0 rational? You can put it over anything, right? But certainly over 1 to get 0. So therefore, it can be expressed as a fraction also. So guess what? This statement is definitely false. Rational numbers do contain all the whole numbers, and they do contain all the counting numbers, okay? Therefore, false statement. All the numbers shown here are irrational. Look at each number carefully. Well, I also have to say that this is false. The reason it is false is there are several numbers there that are rational, not irrational, okay? So I'm going to put false out here, and I want to show you, first of all, I'm going to underline the numbers that are rational. This is rational because it's a repeater. It repeats to infinity. This is rational because it what? It terminates. This is rational because it terminates. Okay? This is rational because it repeats. Okay? So there are two numbers there, however, that are irrational. The one with the arrow on it, remember the arrow indicates to you that the numbers that are decimals that go on forever are all over the place. And of course, this one here is showing a what? A growing pattern, which is an irrational behavior. So there's 1 3, then there's 2 3s, and there's 3 3s, and so forth. So that's the reason why question 3 is false. Let's go on to question 4, true or false question. The number 28.28, 288, 2 followed by 3 eighths, 2 followed by 4 eighths, 2 followed by 5 eighths is both an irrational number and a real number. Well, are irrational numbers real? They are. Are rational numbers real? But yes, they are. But irrational numbers and rational numbers aren't the same kind of number, right? However, this number, being the fact that it is irrational, definitely is also a real number. So that is true. The set -1, 1, -1, 3, -3, 5, -5, 7, -7, ... is the infinite set of odd integers, which is often also listed in this format. Well, when you first saw the odd integers, they were listed in this format, weren't they? Coming in from negative infinity and going out to positive infinity. Well, the first way I showed the set is A-OK, right? Because all we're doing is scrapping numerical order. All the numbers would still be there. You can tell they would be, all right? Because if we go to infinity and follow the same pattern, it would be the same numbers that are located in the second configuration of the set. So this statement is definitely true. When you roll a pair of dice simultaneously, there are exactly 36 outcomes that could result. Well, if you're thinking the answer is 12, you're not right. 6 plus 6 is 12, but no. You have to multiply the number of outcomes together. There are 6 outcomes on the first die, 6 outcomes on the second die, so there are 36 outcomes. So this statement is definitely true. All these numbers listed are counting or natural numbers. Well, unfortunately, there's one number there that is not a counting or natural number. Remember, the counting and natural numbers are the numbers you learned to count with as a kid. You never learned with 0. When you put 0 with the set of counting numbers, you have the set known as the whole numbers. So this is not a counting number. Therefore, this statement is false. Okay, question number 8. In a combination experiment, has 3 individual events which have outcomes which show individual probabilities of 1/2, 3/5, and 7/10 of taking place. As a result, the probability of an outcome of this combination experiment taking place should be 21 out of 100. I'll let the clocks all ring while you think about this. Well, it is correct, because you would multiply 1/2 times 3/5 times 7/10 to get the outcome 21 out of 100. So this is definitely a true statement. Sorry about all the clocks, but I can't see us wasting the time of stopping the video and waiting too much longer. I think you can hear me all right. So you know it's 11 o'clock at night here, but just be aware of the fact for these probability questions, if you know the individual probabilities of each outcome, okay, of the outcomes being discussed in each event, you multiply them together to get the answer that you're looking for. Okay, let's go on. The two sets shown have the same members, the real numbers and the whole numbers. Well, are all real numbers whole numbers? Are all whole numbers real numbers? Yeah, they are. But real numbers have negatives, they have decimals that go on forever, which never repeat or never terminate, which whole numbers don't have. So this is definitely not a correct statement. So number 9 is false. 10. A platonic solid can exist, it should say with 4 squares emitting from a single vertex. I don't know how I got the word "the" in there, but a platonic solid can exist with 4 squares emitting from a single vertex. Let me change this. That's probably wrong on your printout also. Well, what's the story? No, it can't happen. You notice in a cube there are 3 squares emitting from a vertex, not 4. And if you put 4 squares next to each other in a similar configuration like I'm going to show you here, they would be perfectly flat, because those would be all 90-degree angles. So we cannot have 4 squares emitting from a vertex. Sorry about that error on the sheet. All right, 11. Only one platonic solid exists with 3 edges emitting from a single vertex. Well, if you have your platonic fact sheet handy, you might want to look at this, okay? But the answer to this, 3 edges emitting from a single vertex, happens in a cube, right? 3 edges emitting from a vertex also happens in a dodecagon, okay? In a dodecahedron. In a dodecahedron, you have 3 pentagons meeting at a vertex. So you know right away that there has to be at least 2, okay? So cannot be the case, all right? All right, so this is what? False. All these numbers are rational numbers. Well, we can stick this over 1, right? This is a repeating decimal on the end, the negative 39.6351. That's a terminator. That's definitely a mixed fraction. So are all these numbers rational numbers? Absolutely. So that is true. There exist 12 platonic solids. What does your platonic fact sheet tell you? There are only how many? There are only 5. Okay, so this is definitely false. A rectangular prism and a square pyramid are examples of a Platonic solid. Why aren't they? The reason they are not examples of a Platonic solid is that all the faces are not identical, congruent, regular polygons. Therefore, this statement definitely is not true. All the numbers in problem 12 are real numbers. Let's go back up to problem 12. Are all those numbers in there real numbers? Absolutely. Absolutely. They're all a type of real number, okay? 16, so that's a true statement. 16, only one number in problem 12 is an integer. Now, if we go back to the original way I showed the problem, that wasn't there, right? The only integer there is negative 33. So there is only one integer in that group of 4. So that is true. Okay. No negative numbers are rational numbers. Wait a minute. Let's go back up here. Isn't this negative? That's rational. Isn't this negative? That's rational. Okay, so this statement down here is definitely false. Real numbers can have decimal repeaters, decimal terminators, negative decimal repeaters, negative decimal terminators, mixed fractions, negative mixed fractions, integers, whole numbers, or negative mixed fractions. Now, some of those words are a little weird. But can real numbers have all of those different kinds? It most certainly can, right? The only type that's really left out is positive and negative irrational numbers, because all those numbers mentioned there are actually rational numbers. And of course, they are definitely examples of real numbers. So that is definitely a true statement. All these types of questions will be on your final exam, where you will be asked to determine whether the statements are true or false. So I wanted you to get used to seeing the type of problem that I could be asking on the final. Okay, I think we're going to go ahead and do page 3. So let's take a look at that, okay? This is another one of those informal proof ideas. Now, if you were to start with a golden rectangle, at least to 6 decimal places, I want you to prove that once you add the largest square possible to it, the newly formed rectangle is indeed a golden rectangle. You must show your work to verify your answer. Well, gosh, let's see. Well, notice on your figure, on your sheet, I'm sorry, I gave you a figure, which is a what? A golden rectangle. And now what we're going to do is we're going to think a little bit about this. And we're going to cheat just a little. Now, you know, in a golden rectangle, right, its length divided by its width has to be equal to phi, right? Okay, that being said, okay, why don't I call the length and width of this figure phi and 1? How can I get away with that? If I have L over W equals phi, isn't that the same thing as phi over 1? Yeah, it is, right? So I'm going to make the length of this phi, and I'm going to make the width of this 1. Now, what happens if I add the largest possible square to the long end of this golden rectangle? What happens? Well, let me see if I can do this. So I'm going over here. I'm going to add a square to this figure. Here we go. There, I've added a square. Now let me see if I can make it move over just a little bit. Oop, I didn't mean to change pages. Okay, let's go back here. Let me do this. Try to move it over just a little bit. There, that looks better. All right. Now you'll notice I now have, it's kind of hard to see this because I have got a very large picture here in front of you. But notice, if that's a square I put on top, aren't its dimensions for the square phi here, phi right there, phi right there, phi right there? Yeah, they're all phi, right? What's the length of this figure from here to here? Wouldn't it be phi plus 1? And what's the dimension down here across this original golden rectangle? It's phi, right? What are the dimensions length and width-wise on the new figure I have formed? Well, gee, aren't they, the length is phi plus 1. The width is what? Phi. Length divided by width is supposed to be phi. Is phi plus 1 divided by phi going to give us phi again? Well, let's see if it does. Well, if you recall, if you can't recall what phi is, it's probably going to be somewhere else written on the exam. However, it is 1 to 6 decimal places. It's 1.618034. If I add 1 to that and divide it by 1.618034, do I get phi? Well, let's see. If I take 1.618034 and add 1 to it, it's 2.618034. And if I divide that by 1.618034 on a calculator, guess what I get? I get 1.618034 to 6 decimal places. QED. I've done enough to prove that if I add the largest square possible to an existing golden rectangle, the golden rectangle that will be formed with the square and the added, or the original golden rectangle, will also form a new golden rectangle. How about that? Okay. Well, what if I gave you this problem the other way? What do we mean by the other way? Well, what if I said to you this? What if I said to you, if you start with a golden rectangle, prove at least to 6 decimal places that once you remove the largest possible square from it, the leftover rectangle is indeed a golden rectangle. You must verify your answer. Okay? Well, let's start the same way we did before. Let's start with the original figure. The original golden rectangle here is what? It's phi long, because the length divided by the width is phi. So that means it can be said as being phi over 1. So the length of this figure from here to here is phi, right? Its width could be said to be 1, right? Great. If I suck out the biggest square, will the figure left over be a golden rectangle? Can I prove that it will be? Well, let's see. I'm going to take off, all right, this square right here. I'm going to take it off, and I want to make sure that the leftover rectangle on my left is golden. All right, here's what I'm going to do to show it. Okay, if this great big long distance across the top here is phi, what's this distance right here on this part of the square? Isn't it 1? Isn't this 1 right here? Isn't this 1 right here? Sure. So the length of the little golden rectangle is equal to 1. What's the width of the golden rectangle, the little golden rectangle? Well, what is it? It's the distance phi subtracted by what? 1. So in other words, this is phi minus 1, right? Now, what would the length compared to the width be in this figure? It would be length over width, the little guy now I'm talking about, the little rectangle. It would be 1 over phi minus 1, wouldn't it? Well, let's see. What is phi minus 1? Well, let's see. In other words, this should be length over width, 1 divided by 1.618034 minus 1, right? Or in other words, this should be what? Length over width should be 1 divided by 0.618034. So all I have to do is on my calculator, take 1 and divide it by 0.618034. And when I do, guess what? I get 1.6180339, which rounds to 0.34. So in other words, this gives me 1.618034 to 6 decimal places. QED once again, I have shown by informal proof, all right, that this works out, okay? And that I do indeed have a golden rectangle left over when I suck out or take off the biggest square. The same thing was true back here, okay? When I did the same thing here, QED, right? I showed if I add the largest square, okay, I also get phi for length divided by width on that figure. Okay, now I will give you one of these two problems on the final exam. I'm not telling you which one, but you're going to have to informally prove to me one of the two cases involving the golden rectangle. You know it's true, and I want to see if you can come up with how to show it using the various symbols that I have suggested here. Now, folks, we have reviewed a lot of material today. What I'm asking you to do over this weekend is, would you please do exam review sheet 2. It is 4 pages. I would like for you, please, to complete the 4 pages of that sheet, and first thing on Tuesday, we will go over those 4 pages very carefully, okay? Then, after that, we will do some more extra sheets. I have done 3 of the extra sheets with you I believe there are 6 more of them that I will be presenting to you and allowing you to keep to study for the final exam. Okay? So I hope you have a tremendous weekend, relaxing weekend, but I hope you do some work for me. Get the things to me you owe me, and make sure that you're doing okay with all of those. All right? Complete exam review number 2, all 4 pages, and we will do more extras in class on Tuesday. On Thursday, we are going to do a final video quiz, but I'm not going to actually make you do the video quiz. All right, we're just going to go over it together, and then I will send you all the answers to the video quiz after we have gone over it. Well, have a great weekend. I hope everybody's well, and I'll see you all very soon. The weekend will go by quickly. Only about 6 days until the final exam, so go get them. Make sure you study and work hard. Take care.